Welcome to the deep dive. Today we are peering deep inside the notoriously opaque inner workings of large language models. LLMs are amazing at step-by-step reasoning, but those internal steps, well, they're often treated like a black box, even during training.
And that internal opacity creates a major problem for optimization, specifically with reinforcement learning. You see, when an LLM successfully solves a multi-step problem, traditional RL tends to apply a uniform credit or reward across the entire generated sequence. That fundamentally fails to distinguish between the truly critical, pivotal steps in the reasoning and the maybe routine, low-effort continuation steps.
So we're essentially rewarding the model equally for saying therefore and for stating the final derived equation. Bit blunt. But this research changes that. Our mission today is to show how attention dynamics can be harnessed, not just as a pretty visualization, but as a mechanistic blueprint of reasoning itself. We are looking for the intrinsic organizational structure that dictates how LLMs, well, think.
And the researchers, they did succeed in identifying that structure. The central, highly consistent finding is a recurring two-beat pattern that organizes complex LLM reasoning, the Preplan-and-Anchor mechanism. This mechanism is hidden in plain sight within the model's attention maps.
Okay, the pre-plan-and-anchor mechanism. Let's unpack this structural blueprint. The research started by recognizing that not all attention heads are, created equal. They classified them based on their attention span, which they quantified using the attention-weighted mean backward distance. You can think of this distance as simply measuring how far back in the text the attention head tends to look.
And this simple classification immediately separated the attention heads into two highly complementary groups, revealing distinct behavioral patterns. The first group is the local attention heads. These heads maintain a small mean backward distance, meaning they are tightly focused on the immediate recent context, maybe just the last few tokens.
They act almost like the quality control for local phrasing, perhaps.
That's a good way to put it. When you visualize these local heads, they display a characteristic sawtooth pattern right near the diagonal. They intensely track a specific phrasal or semantic chunk, keeping attention highly localized within that chunk.
Okay.
But when that chunk ends, the attention abruptly jumps back to an earlier context to start the next logical phrase. It's a continuous, sort of localized editing process.
Right. And in contrast, the second group, the global attention heads, they have a significantly larger backward distance, indicating frequent long-range dependencies. These heads are the true navigators, then.
They are the architects, maybe, not the editors. These global heads serve to highlight a sparse, small set of key tokens. These are the anchor tokens.
Anchor tokens.
Anchors are powerful because they receive sustained attention from many future positions. They essentially act as semantic pivots, the signposts that literally steer the entire unfolding reasoning process.
That makes sense. So local heads handle the flow, and global heads handle the overall strategy. But we can't train a model based on just visualizing patterns. We need numbers. So how did the researchers translate these attention dynamics into formal, trainable metrics?
Well, to formalize this internal reasoning structure, they developed two novel metrics. They needed a way to measure both the local processing effort and the global strategic importance of every single token generated.
Okay, let's start with the local effort measure. This is the windowed average attention distance, or WAD.
WAD is designed to measure how far back a token looks, but critically, only within a limited or clipped window. They use the last 10 tokens, for instance. This focuses the metric on how much a token relies on context just beyond its immediate neighbors to resolve, say, local ambiguity.
So if the WAD value is low of valley, it means the model is kind of running on autopilot, just continuing a tight local sequence with low cognitive load.
Correct. Low WAD means tight local continuation, indicating low predictive uncertainty. But when the model hits a logical boundary or needs to make a decision, the WAD spikes. That's a peak. That peak signals a sudden, essential long-range consultation, often coinciding with where one semantic chunk ends and the next begins. It's the model momentarily saying, wait, what was the premise of this whole section again? Perhaps.
And if WAD measures the effort a token requires, the second metric measures the impact a token has. That's the future attention influence, or FAI.
FAI is the global importance score. It quantifies how much attention a token receives from subsequent tokens, but within a given horizon. So if a token has high FAI, it means many future tokens refer back to it to guide their generation.
In other words, a high FAI token isn't just an output, it's more like a foundation. It corresponds to key logical waypoints like intermediate calculation results, crucial definitions, or, high-stakes decision points in the reasoning chain.
And this is where they moved beyond just correlation to establishing causality. They empirically validated the importance of these high FAI tokens by running controlled perturbation experiments.
How do they do that?
They took a reasoning sequence and artificially changed a token at a high FAI position, and then compared the resulting subsequent rollout to what happened when they changed a token at a low FAI position.
And the results, I take it, dramatically confirmed FAI's causal role.
They did. When they perturbed tokens identified as high FAI anchors, the resulting reasoning trajectory was substantially derailed. The Jacquard similarity, which is a measure of output overlap, dropped significantly, showing a major break in the underlying logical structure. Indeed. In about 87% of the trials, perturbing a high FAI position resulted in far greater deviation compared to changing a low FAI position. Contrast that with perturbations at low FAI tokens. Changing these sort of filler positions often only affected the local phrasing,
Oh, okay.
preserving the global reasoning path pretty much perfectly.
That distinction is crucial. It means FAI identifies the causal levers of LLM thought. You change the anchor, you change the entire outcome, you change the filler, and the model just adjusts the local grammar and moves on.
This leads directly to the core discovery. Single metrics like WAD or FAI tell us something, but the truly critical insights emerge when you look at their joint dynamics. That's what revealed this consistent pre-plan-and-anchor pattern.
Right, the combined effect. Let's examine those 3 robust coupling patterns they found. The first one is about predictive uncertainty. What happens when WAD peaks?
They found a strong link between WAD peaks and the token's entropy, the model's predictive uncertainty at that point. A spike in WAD signals long-range context retrieval, which seems to be triggered precisely when local cues are insufficient, leading to higher entropy.
So the model has to consult the past because it doesn't really know what to do next based on just the immediate context.
That's the idea. And conversely, low WAD values mean low entropy, highly predictable, or perhaps stereotyped continuations. The model is confident in the immediate next word.
Makes sense. What was the second coupling pattern?
The second coupling pattern provides some cross-validation. They confirmed that the anchors identified by their global SOCIST FAI metric were highly concordant with tokens identified by previous, different research looking at something called receiver heads.
Oh, interesting.
Yes, it confirms that multiple analytical lenses seem to converge on the same sparse set of critical tokens.
Okay. And the third coupling is the rhythm itself. This is the 2-beat dance of the pre-plan-and-anchor.
This is really the centerpiece.
Yeah.
They found that FAI peaks follow or coincide with WAD peaks. Think of it as a 2-step process. First, the model experiences a WAD peak. That's the pre-plan. It pauses, consults long-range context to resolve local ambiguity, and settles on a strategy.
Right.
Second, this long-range consultation immediately generates or coincides with the emission of a token with high FAI. That's the anchor. That anchor token then stabilizes all subsequent reasoning, acting as the definitive commitment to the past the model just decided upon.
So the ambiguity forces the model to look back, the pre-plan, and the outcome of that look back is the commitment token, the anchor. If we know when and where these critical decisions happen, well, what does this allow us to do in training?
It allows us to essentially ditch uniform credit assignment in favor of fine-grained policy optimization. Since we've identified the decision tokens, we can amplify the learning signal specifically for those tokens.
How's that done practically?
They achieve this by scaling the per-token advantage, AD-day, using a coefficient gamma dollar derived directly from these attention signals.
And this required a small technical tweak to make it efficient, didn't it? They needed an auxiliary model, actor at TN, to compute these complex attention maps efficiently in a single forward pass over the generated sequence.
Yes, that allows them to apply the attention-derived coefficients to the policy optimization quite efficiently. They tested 3 novel policy optimization strategies, all using an amplification factor. I think it's 1.5 on the top 40% of the identified critical tokens.
Okay, what were the 3 strategies? The first 2 seem like straightforward applications of the individual metrics. They tested global chunk credit.
Right, that emphasizes those introductory pre-planned tokens identified by large variations in consecutive what-add values, basically, where the model looked back hard.
And they tested global anchor credit.
That simply amplifies tokens with high FAI, the key semantic anchors we talked about.
But the most sophisticated strategy, and the one that really leverages the rhythmic finding, is the coupled rhythm credit.
Hmm.
How did that strategy utilize the relationship between WUD and FAI?
It combined both signals, but with a crucial element of back allocation. Sometimes an anchor token, which is high FAI, is locally dominated, meaning it has a low WUD because the previous token strongly dictated it.
Okay.
When this happens, a fraction of the anchor's highly successful credit is diffused backward to its immediately preceding introductory token, which was the planning step.
That sounds like rewarding the model for its foresight, almost. You're not just rewarding the successful anchor, you're rewarding the planning step that made the anchor, well, inevitable or likely.
That's a good way to think about it. This promotes coherent, chunk-level credit assignment, optimizing the policy to plan better for the necessary anchor.
Now let's look at the payoff, the experimental validation. They tested this across a wide variety of reasoning benchmarks, including the countdown puzzle, cross-sync QA, and some challenging math datasets like A and Olympiad bench. Did it show dramatic differences compared to the uniform credit baseline?
Yes, the key takeaway is the consistent dominance of the coupled rhythm credit strategy. On the challenging countdown benchmark, for example, the coupled strategy achieved 63.1% accuracy. That's a substantial gain of plus 10.5 points over the group relative policy optimization, or GRPO, baseline, which sat at 52.6%.
Wow, that is a massive jump.
It is, simply by rewarding the right 40% of the tokens more strongly.
And the gains weren't isolated to just one task.
No, looking at the Quinn 38B math benchmark, the coupled credit strategy led to pronounced average improvements. For instance, an increase of 5.0 points on AME 25 and 6.3 points on AMC 23. It seems to prove that aligning the optimization signal with the model's internal decision structure really works.
And what about the controls? Did they compare it to similar amplification methods?
Yeah, they did. We also had the critical negative results that underscore the validity of their metric choices. For instance, amplifying credit randomly, or amplifying credit based solely on high entropy.
Did that work?
It provided marginal to no improvement.
Yeah.
Random credit amplification on the Quinn 34B math benchmark, for example, yielded 37.1% average accuracy, identical to the baseline performance. No gain there.
They also performed an ablation study, right, to make the point crystal clear. They deliberately reallocated the credit to the bottom 40% of tokens, those identified as filler or locally dominated, meaning they were low FAI.
Correct. And that experiment resulted in performance degradation. The coupled bottom 40% strategy resulted in an average drop of minus 6.9 points in accuracy across tasks.
So rewarding the unimportant tokens actually hurt performance.
It did. This final result strongly validates that WOD and FAI truly isolate the decisive strategic positions that organize LLM reasoning.
It seems quite evident then that attention dynamics are far more than just a diagnostic tool. They provide a prescriptive measure, revealing this pre-plan and anchor rhythm as the perhaps foundational structure of LLM internal thought.
We've established that the model consistently executes this two-beat rhythm, pausing for a pre-plan, that long-range context retrieval, exactly when local ambiguity is highest, before committing to a global anchor token. This means LLMs don't just generate text token by token, they seem to generate it in planned strategic chunks.
So a final thought for our listeners.
Well, the question for you, the listener, is perhaps what it means for reasoning itself, that the model consistently pauses for this pre-plan look-back exactly when things get ambiguous locally, right before committing to a global anchor token. Is this two-beat rhythm something intrinsic, maybe even fundamental, to how complex reasoning needs to unfold, regardless of whether it's in silicon or, well, somewhere else?